Some stars do not fade quietly. They spend millions, sometimes billions of years burning in the darkness, holding themselves together in a perfect battle between gravity and fire. But eventually, every star begins to run out of time. The fuel weakens, the balance breaks, the core begins to collapse, and what was once a calm point of light becomes one of the most powerful events in the universe. A dying star is not just an explosion. It is the end of an entire cosmic life. It can swell into a red giant. It can shed its outer layers into space. It can collapse into a white dwarf. It can tear itself apart in a supernova. Or, if it is massive enough, it can leave behind something even darker, a neutron star or a black hole. But what would it actually feel like to watch it happen? Imagine standing somewhere impossibly far away, safe from the destruction, watching a star enter its final moments. The light changes first, then the surface begins to swell, then the star becomes unstable, pulsing like a giant heart in space. And finally, the end arrives. Tonight, we are going to witness the death of a star, not as a number in a textbook, but as an experience. The color, the silence, the shockwave, the light crossing space, the terrifying beauty of a star giving its final breath back to the universe. Before we begin, if you enjoy calm, cinematic space documentaries made for sleep, mystery, and deep cosmic questions, make sure to subscribe to Theories Before Sleep, because tonight we are watching one of the most beautiful endings in the cosmos, the moment a star dies and becomes something eternal. Stars feel eternal from far away. They look fixed, calm, almost peaceful. Every night they appear in the same darkness, shining as if they have always been there and always will be. To human eyes, a star can seem like the most permanent thing in the universe. But stars are not permanent. They are born, they live, they age, and eventually they die. Every star you have ever seen in the night sky is somewhere inside its own lifetime. Some are young and burning fiercely. Some are old and swollen. Some are already close to the end. And some of the stars we see may have died long ago, their final light still traveling toward us across space. A star is not a simple lamp in the sky. It is a battle. A star survives because two enormous forces are locked in balance. Gravity pulls inward, trying to crush the star under its own weight. Fusion pushes outward, releasing energy from the core, resisting collapse and holding the star open against gravity. For most of a star's life, this balance is stable, beautiful, almost perfect. This stable period is called the main sequence. It is the long middle chapter of a star's life, the time when hydrogen burns in the core, producing helium and releasing the energy that makes the star shine. Our sun is in this phase right now. It has been shining for about 4.6 billion years, and it is expected to live for roughly 10 billion years in total before it leaves the main sequence. That means our sun is middle-aged, calm by stellar standards, stable, reliable. Every morning we see its light because deep in its core, hydrogen atoms are fusing into helium. This process is nuclear fusion. It is the engine of a star. Inside the sun's core, temperatures and pressures are so extreme that hydrogen nuclei are forced together. When they fuse, a tiny amount of mass is converted into energy. That energy begins a long journey outward, moving through the star's layers until it finally escapes as sunlight. The light that warms your face began as a nuclear reaction in the heart of a star, and that same engine keeps the star alive. As long as hydrogen remains in the core, fusion can continue. As long as fusion continues, outward pressure can resist gravity, and as long as that balance holds, the star remains stable. But not all stars live as long as the Sun. A star's lifetime depends mostly on its mass. Small red dwarf stars burn their fuel slowly. They are dim, cool, and incredibly efficient. Some may live for trillions of years, far longer than the current age of the universe. No red dwarf has had enough time to die naturally yet, because the universe is still too young. Stars like our Sun live for billions of years. They burn steadily, not too fast and not too slowly. They are massive enough to shine brightly, but not so massive that they destroy themselves quickly. Massive stars are different. They are the giants. They burn hot, bright, blue-white. They can shine thousands or even millions of times brighter than the Sun. But that brightness comes at a cost. The more massive a star is, the faster it burns through its fuel. A giant star may contain far more hydrogen than the Sun, but it spends that fuel recklessly. Its core is hotter. Its fusion is faster. Its life is shorter. Some massive stars live only a few million years. A few million years may sound long to us, but for a star, it is almost nothing. They are born, burn violently, and die young. And when they die, they do not leave quietly. They can explode as supernovae, scattering heavy elements into space and leaving behind neutron stars or black holes. But before any star dies, the same essential problem begins. Fuel runs out in the core. For most of its life, a star fuses hydrogen into helium. That is the main sequence phase. But eventually, the hydrogen in the central core becomes depleted. The star still has hydrogen in its outer layers, but the core, the place where pressure and temperature are high enough for fusion, begins to change. This is the first step toward death. And from the outside, at first, almost nothing looks different. The star still shines. Its surface may look calm. Its light may continue crossing space as if nothing has changed. But deep inside, the countdown has begun. The core is no longer the same. Hydrogen fusion weakens in the center. The outward pressure begins to change. Gravity, always waiting, begins to gain ground. The balance that held the star stable for millions or billions of years starts to break. Not loudly, not suddenly, subtly. Deep in the core, gravity squeezes harder. The core contracts. As it contracts, it heats up. Around the exhausted core, hydrogen may continue burning in a shell. This shell burning adds energy to the star's outer layers and begins pushing them outward. The star begins to swell. For a star like the Sun, this is the beginning of its transformation into a red giant. For a massive star, it is the beginning of a far more violent final chapter. But in both cases, the death of a star begins inside. Before the surface changes, before the color shifts, before the star expands, before anything dramatic becomes visible, the first signal is hidden in the core. A quiet failure of fuel, a change in pressure, a slow surrender of balance. This is what makes stellar death so haunting. From far away, you might not notice the moment it begins. If you were watching a star as its core hydrogen ran out, there would be no instant explosion, no sudden darkness, no shockwave, no final flash. The star would continue shining. Planets around it, if any survived nearby, would still see daylight. Comets would still move in long orbits. Dust would still drift through the system. the outside world of the star would appear unchanged. And yet, everything important would already be different. Inside, the star has crossed a threshold. It has begun moving toward an ending it cannot avoid. Gravity does not forget. Fusion does not continue forever. A star can delay collapse for millions or billions of years, but it cannot escape the fact that its fuel is finite. That is the secret every star carries. No matter how bright it shines, it is spending itself. Every second, a star converts mass into energy. Every second, it pays for its own light. Every second, it moves closer to the moment when the fuel that kept it alive begins to fail. For the sun, that moment is still billions of years away, but it will come. One day, the sun's core will run low on hydrogen. The balance will shift. The core will contract. The outer layers will expand. The sun will swell into a red giant, growing so large that the inner solar system will be transformed forever. Earth, if it still exists then, will no longer be the world we know. The oceans will be gone. The atmosphere will change. The sky will burn under a swollen red sun. But that is the fate of a star like ours. A slower death, a long transformation, a shedding of outer layers, a quiet white dwarf left behind. Massive stars follow a more terrifying path. When their hydrogen runs out, they do not simply expand once and fade. Their cores become hot enough to fuse heavier elements. Helium becomes carbon and oxygen. Carbon can burn into heavier nuclei. Neon, oxygen, silicon. Layer after layer forms inside the star. The star becomes like an onion. Different shells burning different elements, each stage faster than the last. Hydrogen burning can last millions of years. Helium burning lasts less. Carbon burning shorter still. By the time silicon burns into iron, the final stage may last only days. Days. After millions of years of shining, the final countdown of a massive star can happen in less than a human lifetime. And iron changes everything. Fusion normally releases energy. That energy supports the star. But iron does not give the star useful energy through fusion. Once an iron core forms, the engine begins to fail completely. The star has reached the end of what fusion can do. Gravity takes over, the core collapses, and the death becomes visible. This is the moment we are moving toward. The moment when a star's quiet inner changes become a cosmic event. But before we witness that final death, we have to understand the life that came before it. A star is born from a cloud of gas and dust. Gravity gathers material. The cloud collapses. The center heats. A protostar forms. Then, when the core becomes hot and dense enough, fusion ignites. A star begins. For millions, billions, or even trillions of years, it shines by holding itself in balance. Gravity inward, fusion outward. A perfect tension. A fire held open by pressure. But every star is a temporary victory against collapse. And the end begins when the fuel changes, when hydrogen runs low, when the core contracts, when the balance weakens, when gravity starts winning. That is the life of a star. A birth from darkness, a long age of fire, a hidden countdown in the core, and finally, a death that can seed the universe with everything needed for new worlds. Because when stars die, they do not simply disappear. They give something back. They create carbon, oxygen, silicon, iron, gold, calcium, and the elements that become planets, oceans, rocks, and living bodies. The atoms inside us were shaped by stars. The iron in our blood, the calcium in our bones, the oxygen we breathe, the carbon in every cell. Some of it came from stars that lived, burned, and died long before the sun was born. So tonight, when we witness the death of a star, we are not only watching destruction, we are watching transformation. The end of one star can become the beginning of something else. A nebula, a white dwarf, a neutron star, a black hole, a new generation of stars, a future planet, maybe even future life. But first, we must watch the balance break. We must follow the star from its calm main sequence life into its final instability. We must see what happens when the core runs out of fuel, when gravity begins to win, and when the star that once seemed eternal finally enters its last chapter. Tonight, we witness the death of a star. From beginning to end, every quiet change, every terrifying collapse, every beautiful release of light, and every final moment when a star gives its last breath back to the universe. To watch a star die, we first have to choose the star, because not all stars die the same way. Some stars fade slowly, almost peacefully, shedding their outer layers into space like glowing smoke. Others end in violence. They collapse under their own gravity and explode with enough energy to outshine entire galaxies. The death of a star depends on what kind of star it was while it lived. A star like our Sun does not die in a supernova. It is not massive enough. Its ending is slower, quieter, and strangely beautiful. It swells into a red giant, loses its outer atmosphere, creates a glowing planetary nebula, and leaves behind a small, hot, dense core called a white dwarf. That is the graceful death. But a massive star dies differently. A star many times heavier than the Sun burns faster, lives shorter, and ends in catastrophe. Its core collapses. Its outer layers are blasted into space. A supernova is born, and what remains may become a neutron star or a black hole. That is the violent death. Tonight, to truly understand what it would feel like to watch a star die, we will witness both. First, we will watch a sun-like star enter its final transformation. A slow cosmic ending, a star swelling, fading, and releasing its outer layers into the darkness. Then we will turn toward a massive star, a giant reaching the final seconds of its life, a star whose core has already begun the final collapse, a star that will not fade gently, but tear itself apart in light. But before we can witness any of this, we need one more thing: distance. Because a dying star is beautiful only if you are far enough away. Too close, and beauty becomes destruction. For a sun-like star, the danger grows slowly. As it expands into a red giant, nearby planets may be scorched, swallowed, or stripped of their atmospheres. The heat increases. The star grows enormous. Space around it becomes filled with unstable winds and glowing gas. To observe that kind of death safely, we would need to remain far beyond the reach of the expanding outer layers, far enough that the star's radiation and charge particles cannot destroy our instruments. But a supernova is different. A supernova is one of the most powerful explosions in the universe. The light alone can be blinding across interstellar distances. The shockwave expands outward at incredible speed. High-energy radiation floods space. Gamma rays, X-rays, ultraviolet light, cosmic rays, and neutrinos all erupt from the dying star. To survive watching a supernova, we could not be near it in the way we imagine being near a planet or moon. We would need to be far away, very far. A supernova within a few dozen light years of Earth could be dangerous to life, depending on its type, direction, and energy. To observe safely, we would choose a distance of hundreds of light years or more, far enough to survive, close enough to see the event clearly with advanced instruments. Human eyes alone would not be enough. A star's death happens across every wavelength of light. Visible light is only part of the story. The first warning from a massive star may not arrive as light at all. It may arrive as neutrinos, ghostly particles created deep in the collapsing core. Neutrinos escape the star before the visible explosion breaks through the surface. They are almost impossible to stop, passing through planets, spacecraft, and human bodies as if matter were nearly empty. If we wanted to witness the death properly, our observation platform would need neutrino detectors. It would need gamma-ray sensors, X-ray telescopes, ultraviolet cameras, infrared imagers, radio antennas, spectrometers to read the chemical fingerprints of the explosion, gravitational wave detectors if the collapse is violent enough to ripple space-time, and high-resolution optical telescopes to capture the moment the star changes in visible light. We would not use a small spacecraft. We would need an observatory, a deep space observation platform built like a silent island in the dark. Imagine it drifting far from any planet, its hull shielded against radiation, its instruments spread across long arms to avoid interference. Huge mirrored telescopes pointed toward the dying star, radio dishes listening, magnetic shields humming quietly, computers waiting for the first sign. Inside, there are no windows like a normal spaceship. Windows would be useless against the full violence of stellar death. Instead, the star is watched through screens, sensors, filters, and instruments designed to survive brightness no human eye could endure directly. The observatory does not sleep. It watches in every direction. It measures temperature, pressure, spectra, radiation, particle flow, and changes in the star's outer atmosphere. It waits, because a star can look stable from outside long after the inside has already changed. That is the strange thing. When we arrive at our observation position, the star in front of us may still appear calm, ancient, enormous, beautiful. If it is the sun-like star, it may glow warm, yellow-white, still holding the memory of its main sequence life. But deep inside, the core is already changing. Hydrogen has run low. The balance has begun to shift. Gravity has started squeezing the center. The outer layers are waiting for the energy that will soon make them expand. From far away, the star does not yet look dead. It looks alive. That is what makes the moment so haunting. Death begins invisibly. There is no announcement, no sound, no clear line between ordinary life and final transformation. Only tiny changes at first, a slight swelling, a subtle shift in color, a change in brightness, a change in the spectrum. The instruments see it before the eye ever could. The star is leaving the main sequence. Its long, stable life is ending. And now, the graceful death begins. But somewhere else, in another region of space, a massive star is also waiting. This one is different. It is not calm. It is enormous, unstable, and burning through its final fuels. Inside it, the core has become layered like a cosmic furnace. Hydrogen burns in one shell, helium in another. Carbon, neon, oxygen, and silicon burn deeper in the star, each stage faster and more desperate than the last. By the time we point our observatory toward it, the star may already be close to the end. Its outer surface may look huge and red, or hot and blue depending on the type of massive star it became. It may pulse. It may shed material into space. It may be surrounded by clouds of gas lost during its final unstable years. Around it, the space is not empty. It is filled with the star's own past, layers of material thrown off before the final death. The star has been warning the universe for a long time, but the final signal comes from the core. And the core is hidden. No telescope can see directly into the center of the star. The outer layers hide the final drama until the last moment. But our instruments can sense the signs, changes in the star's light, shifts in its outer gas, neutrinos building quietly in the detectors. The star is dying from the inside outward, and we are watching from far away, knowing that what appears peaceful is no longer safe. There is something deeply unsettling about choosing a star to die, because in a way, the star was chosen long before us, by its mass, by its birth cloud, by the amount of gas gravity gathered when it formed. A small star was given a long, quiet life. A sun-like star was given billions of years of steady fire. A massive star was given brightness, power, and a short, violent destiny. Every star carries its death inside its birth. The ending is written into the beginning. And now, from our observation platform, we are not changing anything. We are only witnesses. The star does not know we are there. It does not know it is being watched. It does not feel fear. It does not understand beauty. It simply follows physics. Gravity pulls, fusion burns, fuel runs out, the core changes, the balance breaks, and the universe prepares for one of its oldest rituals, a star returning itself to space. For the sun-like star, the final act will be slow, glowing, and almost gentle. For the massive star, the final act will arrive like a cosmic scream made of light. Both are deaths. Both are beautiful. Both are terrifying. And both remind us that the universe creates by destroying. The oxygen we breathe, the carbon in our bodies, the iron in our blood, the calcium in our bones, all of it comes from stars that lived and died before us. So as we take our position in the darkness, watching the first star before us, we are not only watching an ending, we are watching the beginning of future worlds. The observatory turns silently. The instruments lock onto the star. The screens brighten. The sensors begin recording. In front of us, the star still shines, ancient and enormous, calm to the eye, but already deep inside, dying. The first death we witness is not an explosion. Not yet. It is slower than that, quieter, more patient. A sun-like star does not suddenly tear itself apart. It does not collapse in one final second. It does not flash into a supernova and vanish into the dark. Its death begins deep inside, where no eye can see. For billions of years, the star has survived by burning hydrogen in its core. Hydrogen atoms fused into helium, releasing energy, creating pressure, and holding gravity back. This was the long, stable life of the star, the main sequence, the peaceful middle chapter, when the star looked almost eternal from the outside. But now, at the center, the hydrogen is almost gone. The core that once burned steadily has become filled with helium ash. Fusion weakens. The outward pressure begins to fall, and gravity, waiting patiently for billions of years, starts to win. At first, nothing dramatic happens on the surface. From our observation platform, far away in the darkness, the star still shines. It still looks familiar, warm, golden, stable, but our instruments know better. The spectrum is changing. The internal balance is failing. The core is contracting. As gravity squeezes the helium core inward, the temperature rises. The pressure increases. the star is not dead yet. It is changing into something larger, stranger, and more dangerous. Around the shrinking core, hydrogen still remains in a shell. This shell becomes hot enough to burn. Fusion moves outward from the center into the surrounding layers, and that shell burning releases new energy into the star. The outer layers begin to respond. They expand, slowly at first, then dramatically. The star begins to swell. This is the beginning of the red giant phase. A star that once looked calm and compact begins growing to hundreds of times its original size. Its outer atmosphere stretches outward into space. Its surface moves farther and farther from the core. The star becomes enormous, loose, unstable, and breathtaking. If this were our sun, the inner solar system would be transformed beyond recognition. Mercury would disappear first, then Venus. Earth's fate would be uncertain in the strictest physical sense, but nothing living here would survive. Our oceans would boil away. The atmosphere would be stripped and broken. The surface would be burned, dried, and sterilized under a swollen, dying sun. The blue planet would become a memory. That is what a red giant means to nearby worlds. Not an explosion, a slow approach of impossible heat. The star expands so widely that its surface actually cools. That sounds strange. The core is becoming hotter, but the outer surface is spreading into a much larger area. The energy is distributed across an enormous shell, and the visible surface temperature drops. The color shifts. The familiar yellow-white glow fades. Orange begins to appear. Then red, deep, dark, ancient red. From a safe distance, the star is no longer a bright point. It is a presence. A huge red sphere hanging in space, swollen and dimmer in color, but far more luminous overall. Because even though the surface is cooler, the star has become so enormous that it gives off much more total light. It is like a dying fire spreading across the sky, cooler at the surface, but larger than anything it ever was before. Our observation platform waits at a safe distance, far beyond the destroyed inner worlds. The star fills a massive part of the sky now. Not a small disk, not a distant sun. A red giant so large that it seems to dominate the entire system. Imagine looking out from the observatory and seeing it fill a quarter of the sky. A huge red wall of fire. Its surface is not smooth. It boils slowly with enormous convection cells, each one larger than planets. Darker patches drift across the star's outer atmosphere. Huge plumes of gas rise and fall. The star breathes unevenly, expanding and contracting, pulsing as its interior searches for balance. Around it, space is filled with material. The star is losing mass. A slow stellar wind carries gas outward into the system. What was once part of the star is now drifting into space, forming a faint envelope around it. Dust may begin to form in cooler regions of the expanding atmosphere. The dying star starts giving itself back to the universe long before the final act. From far away, it is beautiful. From close up, it is destruction. Any nearby planet would experience the end of habitability long before the star's outer layers arrived. First, the light would grow stronger over millions of years. The climate would destabilize. Ice would vanish. Oceans would warm. Then the oceans would begin to evaporate faster than rain could restore them. Water vapor would fill the atmosphere, creating a runaway greenhouse effect. The sky would become heavy, bright, and unbearable. Eventually, the oceans would boil, not in a single instant, but as part of a long planetary death. The atmosphere would be changed by heat and radiation. Molecules would break apart. Hydrogen would escape into space. The planet would dry out, then bake, then lose the last traces of its old surface life. If there had been forests, they would be gone. If there had been oceans, they would be gone. If there had been cities, they would become silent beneath the expanding light. A sun-like star dies beautifully, only from a distance. For its planets, the beauty is lethal, and yet the star is not finished. Deep inside the red giant, the helium core continues contracting and heating. The star has changed because hydrogen fusion moved into a shell, but the helium in the core has not yet begun its own burning. For a while, the core is like a compressed ember, hotter, denser, waiting. Then comes one of the strangest moments in the life of a sun-like star, the helium flash. When the core becomes hot enough, helium nuclei suddenly begin fusing into carbon and oxygen. In stars like the Sun, this ignition can happen extremely rapidly inside the core. A huge amount of energy is released in a short time, but from the outside, the helium flash may not look like a gigantic explosion. The energy is trapped deep inside. The star absorbs it. The core expands. The internal structure changes. Still, across the star, the event is violent and profound. A hidden ignition, a sudden awakening. The star, which had been drifting toward instability, finds a temporary new balance. Helium fusion now burns in the core. Hydrogen continues burning in a shell around it. The red giant settles. For a while, it becomes calmer. This phase is sometimes called the horizontal branch for certain stars, or a related stable helium burning stage. It is not youth returning. It is not rescue. It is a pause, a false calm before the final act. From our observation platform, the star seems less chaotic for a time. Its outer behavior becomes more stable. Its brightness changes. Its structure has reorganized. It has found a new way to resist gravity, but only temporarily, because helium, too, is fuel, and fuel always runs out. The star now carries the products of its own aging inside it. Hydrogen became helium. Helium begins becoming carbon and oxygen. The core becomes heavier, more complex, less able to continue the old battle forever. Gravity never leaves. It only waits for the next weakness. Around the star, the remains of nearby planets continue their silent transformation. Any close rocky worlds are now dead surfaces, oceans gone, atmospheres damaged or lost, crusts baked and fractured, moons scorched, rings of debris altered by radiation and stellar wind. Farther out, icy worlds made briefly warm. Moons that were frozen for billions of years might melt for a short time. Subsurface oceans could rise closer to the surface. Distant planets may receive more light than ever before. For a brief cosmic moment, the habitable zone moves outward. Worlds that were once frozen might feel the dying star's warmth. But this is not a new beginning. It is a temporary gift from a dying system. The red giant's brightness will not remain stable forever. Its outer layers will become increasingly unstable. Its winds will strengthen. Its pulses will grow. Its body will begin to loosen. The star is preparing for its final beautiful act. From our safe distance, the sight is almost impossible to describe. A star that once burned steadily has become a vast red giant. Its color is deeper. Its size is monstrous. Its atmosphere moves like a slow ocean of fire. Its light fills space with an ancient glow. It looks powerful, but it is fragile. The star is no longer the balanced engine it once was. It is a dying structure, held together by temporary stages, burning new fuels in desperate sequence, shedding mass into space as if it is already becoming something else. And in a way, it is. The star is not simply dying, it is transforming. The carbon and oxygen in its core may one day remain as a white dwarf. The gas it sheds may become a glowing nebula. The material released into space may mix with interstellar clouds. Some of it may one day become part of new stars, new planets, maybe new oceans, maybe life. That is the strange mercy of stellar death. It destroys the worlds closest to it, but gives future worlds the ingredients to exist. The red giant before us is not the final image. It is the middle of the ending. The core has changed. The surface has swollen. The color has deepened. The planets nearby have been ruined. The helium flash has passed. The star has entered its false calm. But the end is still ahead. Soon, its outer layers will become unstable beyond recovery. Soon, the star will begin to cast itself into space. Soon, the final glowing shell will form around the exposed core, and what began as a quiet yellow-white star will become one of the most delicate and beautiful graves in the universe. For now, we watch. The observatory drifts in silence. The red giant fills the sky, ancient, enormous, dying, and already, deep inside, the final act has begun. The false calm cannot last forever. For a while, the dying star found a new balance. Its core burned helium. Its outer layers expanded and cooled. The star became a red giant, ancient and enormous, glowing like a deep red ember in the darkness. But helium is also fuel. And eventually, that fuel begins to run out. Deep inside the star, helium fusion weakens. The core, now rich in carbon and oxygen, can no longer support itself the way it once did. It begins to contract again under gravity. The pressure rises. The temperature rises. But for a sun-like star, the core will never become hot enough to fuse carbon in a stable way. This is the limit. The star has reached the end of what it can burn. It cannot become a supernova. It cannot forge heavier and heavier elements like a massive star. It has no violent iron core waiting to collapse. Instead, it enters a different kind of death, a slow unraveling. The outer layers become unstable. The star begins to pulse. From our observation platform, see the red giant changing again. Its surface swells, contracts, and swells once more. The star is no longer steady. It breathes in huge, slow waves, as if the entire outer atmosphere is rising and falling in a final rhythm. These are thermal pulses. Deep inside the star, unstable shell burning releases bursts of energy. That energy moves outward, shaking the outer layers and sending shells of material into space. The star begins to shed itself. At first, it looks like a faint wind, a soft stream of gas flowing away from the surface. Then the mass loss grows stronger. The star's outer atmosphere loosens. Layer after layer drifts outward into the darkness. What once belonged to the star is no longer held tightly by gravity. The dying star is becoming transparent to its own ending. It is giving away its body. Shells of gas expand into space at tens of kilometers per second. That sounds fast, but on the scale of stars, it is graceful. Not an explosion like a supernova, not a sudden blast, more like a glowing exhale, a final breath. The star's outer layers move outward, forming an expanding envelope around the shrinking core. Hydrogen, helium, carbon, nitrogen, oxygen, and dust spread into space. The material forms rings, bubbles, arcs, and delicate filaments. From far away, it begins as a faint halo. Then it grows. The star continues losing mass until, finally, their outer layers are gone. The core is exposed, and at the center of the expanding cloud, something tiny appears, a white dwarf. It is the leftover heart of the star, small, dense, and impossibly hot. A white dwarf can be roughly the size of Earth, yet contain a large fraction of the mass of the original star's core. It is not burning fuel anymore in the normal way. It is not alive as a star once was. It is the compressed remnant left after fusion has ended. But it is still extremely hot, so hot that it floods the surrounding gas with ultraviolet radiation. That radiation changes everything. The expanding shell of gas around the star is still there, drifting outward into space. At first, much of it may be dim and almost invisible, but when ultraviolet light from the white dwarf strikes the gas, atoms become ionized. Electrons are stripped away, then recombine, releasing light. The nebula begins to glow. This is the birth of a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers called them planetary nebulae because through small telescopes, some looked like round planetary disks. But they are not planets. They are the ghosts of dying stars, the outer layers of a star like the sun, lit by the exposed core left behind. From our observation point, the transformation is breathtaking. Where there was once only a red giant, there is now a glowing cloud expanding into space. The white dwarf burns at the center like a tiny blue-white jewel. Around it, gas spreads outward in a delicate shell, becoming brighter as radiation passes through it. Color begins to appear, not painted, not decorative, but physical. Different elements glow in different ways. Hydrogen can shine red. Oxygen can glow green or blue-green. Nitrogen can glow in deep orange and red. Helium adds its own pale light. The nebula becomes a cosmic lantern made from the star's own lost atmosphere. And the structure is not perfectly smooth. It forms shapes, rings, bubbles, twin lobes, spirals, knots, thin filaments like silk. Some parts move faster than others. Some regions are shaped by magnetic fields. Some are sculpted by winds from the white dwarf. If the star had a companion star, gravity may stretch and twist the gas into even stranger forms. What we see is not a simple sphere. It is a work of physics, a final sculpture made by radiation, motion, chemistry, and death. The most beautiful sight in the universe begins forming before our eyes. And it is beautiful because it is temporary. A planetary nebula does not last forever. It expands for tens of thousands of years. To human beings, that sounds eternal. But to the universe, it is brief. A glowing shell appears, shines, spreads, and slowly fades into the surrounding space. We know many examples of these stellar ghosts. The Ring Nebula, a glowing circle in Lyra, like a smoke ring left behind by a dying star. The Helix Nebula, sometimes called the Eye of God, a vast nearby planetary nebula with a white dwarf at its center, surrounded by glowing layers of gas. The Cat's Eye Nebula, complex, sharp, and strange with delicate shells and patterns that look almost designed, though they were created only by the physics of a dying star. Each one is the remnant of a star that ended like this, a sun-like star, a star that exhausted its fuel, a star that expanded into a red giant, a star that shed its outer layers, a star whose exposed core lit the gas from within. When we look at planetary nebulae, we are not seeing random clouds. We are seeing the final artwork of stars, We are seeing what happens when a star dies gently enough to leave beauty behind. From our platform, the nebula grows wider year after year. The shell expands outward into the dark. The gas becomes thinner as it spreads. The colors shift. Bright knots form and drift apart. The central white dwarf remains fiercely hot, pouring ultraviolet light into the fading envelope. The star is no longer a star in the old sense. It has no vast outer atmosphere, no hydrogen-burning core, no red giant surface. Only the remnant remains, a hot core surrounded by its own memory. If there were planets far away from the star, they would see a sky transformed. Their old sun would no longer be a red giant filling the heavens. Instead, the center of the system would glow with a tiny white-hot point surrounded by a vast, colorful shell. The system would be quiet now. The inner planets may be gone or ruined. The outer worlds would orbit a dying remnant, and all around them, the remains of the star would drift through space like illuminated mist. It would feel less like an explosion and more like the universe holding a memorial. But even this beauty fades. As the nebula expands, the gas becomes more diffuse. The atoms grow farther apart. The glow weakens. The white dwarf slowly cools. Its ultraviolet radiation becomes less intense. The shell loses its brightness and begins blending into the interstellar medium. After tens of thousands of years, the planetary nebula becomes faint. After longer still, it disappears into the galaxy. The gas does not vanish. It becomes part of space again. It mixes with other gas and dust. It may one day become part of a new molecular cloud. That cloud may collapse into new stars. Around those stars, new planets may form. The material from the dead star may become rock, atmosphere, ocean, life. This is why the death of a sun-like star is not only an ending, it is recycling on a cosmic scale. The star cannot continue. Its core has become a white dwarf. Its outer layers are gone, but the matter it released is now free. The oxygen glowing in the nebula may one day become air. The carbon may become organic chemistry. The nitrogen may become part of living cells. The dust may become planets. Death becomes material. Material becomes worlds. Worlds may become life. And life may one day look up and see the nebulae left by other dying stars. There is something deeply peaceful about this kind of stellar death. It is destructive to nearby worlds, yes. It is the end of a solar system as it once was, but it is not meaningless destruction. It is transformation. The red giant becomes a nebula. The core becomes a white dwarf. The outer layers become a glowing shell. The shell becomes interstellar gas, and the gas becomes part of the next generation. From our observation point, we watch the ghost of the star expand, slowly, silently, beautifully. The white dwarf burns at the center, small but intense, like the final ember of a cosmic fire. Around it, the nebula glows in red, green, blue, and orange. The colors ripple through space as the shell spreads wider. This is what a sun-like star leaves behind. Not a bang, not a black hole, not a violent collapse, but a delicate luminous grave, a final flower of gas opening in the darkness. And one day, the nebula will fade, the white dwarf will cool, the system will become quiet. But for a brief moment in cosmic time, the star has become more beautiful in death than it ever was in life. A ghost of light, a shell of color, a reminder that even the gentlest ending in the universe can be terrifying and beautiful at the same time. After the nebula fades, almost nothing remains. The great red giant is gone. The glowing shell of gas has drifted outward into space. becoming thinner, dimmer, and harder to see. The colors fade first. The red hydrogen weakens. The green-blue oxygen dims. The delicate filaments dissolve into the darkness. What was once one of the most beautiful sights in the universe becomes a faint memory, a ghost losing its shape. And at the center of that fading cloud, the dead star remains, not as a giant, not as a glowing nebula, not as a burning sun, but as a white dwarf. A white dwarf is the compressed core of a star that has finished its life. It is what remains after a sun-like star has exhausted its fuel, expanded into a red giant, shed its outer layers, and exposed the dense center that was hidden for billions of years. From far away, it looks small, almost innocent, a tiny white point in space. But this tiny remnant is one of the densest objects in the universe. Imagine an object roughly the size of Earth, but containing a mass comparable to the Sun. That is a white dwarf, a whole star's core compressed into a sphere about the size of a planet. The gravity at its surface would be crushing. The density is almost impossible to imagine. Matter inside a white dwarf is packed so tightly that atoms are forced into a strange state. Electrons are squeezed together, creating a pressure that prevents the star from collapsing further. This is not normal matter as we experience it. It is stellar matter under extreme compression. A teaspoon of white dwarf material could weigh tons. In many descriptions, a spoonful can weigh several tons, sometimes even more, depending on the white dwarf. Something that would fit in your hand would be heavier than a truck. That is what remains of the star. Not flame, not fusion, density, silence, heat. A white dwarf does not shine because it is still burning fuel like a normal star. Its nuclear engine is gone. Hydrogen fusion has ended. Helium fusion has ended. The star cannot create new energy in the way it once did. It shines only because it is still hot. It is glowing with leftover heat from its former life, the heat trapped inside it when the core was compressed and exposed. It is like a coal removed from a fire, still burning white hot, but no longer producing new flames. The white dwarf is not alive as a star anymore. It is cooling, slowly, patiently, across time spans so long they barely fit inside human thought. At first, it is incredibly hot. Its surface can glow white or blue-white, pouring ultraviolet radiation into the remains of the planetary nebula around it. That radiation is what made the nebula shine in the first place. But as the nebula disappears, the white dwarf remains alone, a bright dot in a dark system. The planets nearby, if any survived, now orbit a stellar corpse. The once powerful star has become small enough that its old solar system feels empty around it. The warmth is weak compared to the star's younger days. Worlds that once received sunlight now drift in colder orbits. Frozen moons and distant planets continue circling. But the age of normal daylight is over. From our observation platform, the change is heartbreaking. We watched the star swell into a red giant. We watched it shed its outer layers. We watched the nebula form like a flower of light. And now, after all that beauty, only the white dwarf remains. Small, brilliant, alone. This is the final state of a star like our Sun. Not a supernova, not a neutron star, not a black hole, a white dwarf, a quiet ember of stellar matter, slowly releasing the last heat of a life that lasted billions of years. There is dignity in that ending. A sun-like star does not die with violence. It does not tear the galaxy open It does not collapse into a monster. It simply burns for billions of years, gives light to whatever worlds formed around it, then slowly releases its outer layers and settles into silence. It is not dramatic in the way a supernova is dramatic, but it is profound, because this is how our own sun will end. One day, billions of years from now, the sun will become a red giant. It will transform the inner solar system. It will shed its atmosphere into space. It may create a planetary nebula, and at the center, where the sun once burned with steady yellow light, there will be a white dwarf, a tiny remnant, hot, dense, quiet, the object that used to be the sun. And then the long cooling will begin. A white dwarf cools over billions and trillions of years. It radiates its heat into space, slowly becoming dimmer and colder. There is no new fuel to replace the energy it loses, no fusion to restart the star, no final hidden engine waiting to awaken, only fading. At first, it glows white. Then, over unimaginable time, it becomes yellowish, then orange, then red, then infrared, then dark. Eventually, after trillions upon trillions of years, a white dwarf is expected to become a black dwarf, a cold, dark stellar remnant that no longer gives off meaningful light. But the universe is not old enough for black dwarfs to exist yet. The cosmos is about 13.8 billion years old. White dwarfs need far longer than that to cool completely, so every black dwarf belongs to the future. A future so distant that no human civilization can easily imagine it. A future after the current age of stars. A future when many bright suns have burned out, when galaxies have aged, when the universe has grown darker and colder. In that future, black dwarfs may drift through space like dead coals, cold, dark, silent, the final cooled remains of stars that once shone for billions of years. Imagine a universe filled with them. No bright constellations, no glowing spiral arms full of young blue stars, no star-forming nebulae lighting up in pink and gold, only old remnants, white dwarfs fading into black dwarfs, neutron stars cooling, black holes waiting, planets frozen in darkness, galaxies dimmed into shadows of what they once were. A black dwarf universe would be almost impossible to recognize. The night sky would not be alive with stars. It would be nearly empty, not because matter disappeared, but because the light went out. Stars are temporary fires, and eventually, all fires spend their fuel. In that ancient future, the remains of sun-like stars would drift invisibly through the dark. They would still have mass, still have gravity, still exist, but they would no longer announce themselves with light. They would be the quiet bones of the stellar age, cold cinders from a brighter universe. This is the ultimate fate of stellar matter for stars like the sun. Not destruction in one moment, not a final scream, a slow retreat from light. The white dwarf is the beginning of that retreat. It is still beautiful when it first appears, shining with the heat of everything it once was. But its beauty is not the beauty of life. It is the beauty of memory. It glows because it was once a star. It shines because it has not yet forgotten its heat. It is the last visible proof that a sun once lived there. And for trillions of years, it will continue to fade. That kind of timescale changes the feeling of death. For us, death feels sudden because human lives are brief. But for a star like the sun, even death is long. The main life lasts billions of years. The red giant phase lasts millions more. The planetary nebula shines for tens of thousands. the white dwarf cools for trillions. A star does not disappear. It withdraws, slowly, carefully, almost gracefully. From our safe observation point, we watch the white dwarf at the center of the old nebula. Around it, the last traces of gas continue spreading outward, becoming part of the galaxy. The glowing shell fades into invisibility. The surrounding darkness returns. The star's great display is over. No more swelling red surface. No more thermal pulses. No more glowing nebula. Only the tiny core remains, holding the compressed history of a sun. It is smaller than the star was by almost an impossible amount. But in a strange way, it feels heavier now. Not physically only, emotionally. Because everything the star was has been reduced to this point of light. All its ages, all its fusion, all its warmth, all the planets it may have held, all the mornings it may have created, now gathered into a single white ember. The death of a sun-like star is not terrifying because it explodes. It is terrifying because it shows how even the gentlest stars are temporary, even the stars that give life, even the stars that seem calm, even the stars we trust every day without thinking. They are all burning through their time, and one day each will leave behind only a remnant, a white dwarf, then, much later, a black dwarf, a cold, dark cinder drifting through space. But there is peace in it too, because the star did not vanish without meaning. It gave light for billions of years. It shaped worlds. It forged elements. It released its outer layers into the galaxy. It left behind material that may someday become part of something new. And then, when its great work was done, it cooled. Quietly, with a dignity that only deep time can hold. The white dwarf before us shines alone now, a small white point in the darkness, no longer a star of life, not yet a black dwarf of the far future. It is between fire and silence, between memory and darkness, the final ember of a star that once burned like a sun. And as we watch it fade, we understand something gentle and terrible at the same time. Some stars die in explosions, some die in beauty, and some simply spend the rest of eternity cooling in the dark. We leave the white dwarf behind, the quiet ember, the gentle ending, the slow fade into darkness. And now, our observation platform turns towards something far more dangerous, a different star. A heavier star, a star that was never meant to live for billions of years. This one is massive, about 20 times the mass of our sun. From far away, it looks magnificent. A huge burning giant suspended in the dark, brighter than almost every star around it. It has lived with impossible intensity, pouring energy into space at a rate our sun could never match. But that brilliance came with a cost. A star like this does not live calmly. It burns too hot, too fast, too violently. While our sun can shine for around 10 billion years, this massive star may live only around 10 million. 10 million years. That is long compared to a human life, but almost nothing compared to the lifetime of a sun-like star. It was born after many older stars had already died. It ignited in a cloud of gas and dust, shone with furious blue-white light, carved a cavity in the nebula around it, and burned through its fuel like a fire that knew it had no future. And now, already, it is dying. But it will not die gently. This star will not become a quiet planetary nebula. It will not shed its layers slowly and leave behind a peaceful white dwarf. This star is heading toward collapse, toward supernova, toward one of the most violent endings in the universe. Our platform moves into position at a safe distance, far enough to survive the radiation and shock, close enough for the instruments to capture everything. 50 light-years away, the star is still dangerously bright, but not close enough to destroy the observatory instantly. Every shield is active. Every detector is ready. The telescopes are pointed directly at the dying giant. Neutrino sensors wait in silence. X-ray instruments are armed. Gamma-ray detectors sleep lightly, waiting for the first impossible flash. From here, the star still looks almost normal. That is the terrifying part. It shines, it glows, it looks alive. A huge star in the darkness, ancient in appearance, powerful, enormous, still giving light to the space around it. But inside, the countdown has reached 0. Deep in its core, the star has been changing for a long time. A massive star does not stop after burning hydrogen. When hydrogen runs low, it begins burning helium. When helium is exhausted, it burns carbon, then neon, then oxygen, then silicon. Each new stage happens faster than the last. Hydrogen burning lasts millions of years. Helium burning lasts much less. Carbon burning may last hundreds or thousands of years. Oxygen and neon burn faster still. And silicon burning, the final stage before disaster, may last only days. Days. After millions of years of life, the final fuel stage of a massive star can pass almost like a final breath. Inside the star, the structure has become layered. It is no longer one simple core. It is like an onion made of fire. Hydrogen burns in an outer shell. Helium burns beneath it. Carbon, neon, oxygen, and silicon burn closer to the center. Each shell creates heavier elements. Each shell adds pressure. Each shell tries to keep gravity away for just a little longer. But at the very center, something fatal is growing. Iron. Iron is the end of the road. For most of a star's life, fusion releases energy. When hydrogen fuses into helium, energy comes out. When helium forms carbon and oxygen, energy comes out. For massive stars, heavier elements can keep forming, and each stage gives the core another temporary source of support. But iron is different. Iron does not help the star. Fusing iron does not release useful energy. Instead, it consumes energy. That means once the core fills with iron, the star has created a poison at its own center. A dead weight, a final ash, a core that cannot burn its way out of collapse. The star is now carrying its own ending inside it. The iron core grows as silicon burning continues around it. More and more iron group elements collect in the center. The core becomes denser, heavier, more unstable. For a while, it is supported by electron degeneracy pressure, a strange quantum resistance that can hold matter up even when normal thermal pressure fails. But there is a limit, the Chandrasekhar limit, around 1.4 times the mass of the Sun. If the iron core grows beyond that, it can no longer support itself. Gravity wins completely, and when gravity wins in a massive star, it does not win slowly. It wins instantly. From the outside, nothing has changed yet. The surface is still shining. The outer layers still glow as if the star has time. A planet orbiting far away might still see its sun rise. A distant observer might still think the star is alive. But deep inside, the iron core has reached the limit. The final balance fails. The center of the star begins to collapse. Everything that follows happens in less than 1 second. 1 second. That is all it takes for a giant star to move from life to catastrophe. The iron core, once supported, suddenly falls inward. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos. Matter accelerates toward the center at a significant fraction of the speed of light. the core collapses from thousands of kilometers across to something only tens of kilometers wide. A star's heart becomes a neutron star in an instant. Or if the mass is great enough, the collapse may continue toward a black hole. The density becomes almost unimaginable. Atomic structure fails. Matter is compressed beyond anything ordinary physics can describe casually. The inner core stiffens suddenly as nuclear forces resist further compression. The infalling material rebounds. A shockwave forms. But at first, the shock struggles. It loses energy. It stalls. The star fights against its own explosion. Then, the neutrinos arrive. An enormous burst of neutrinos floods outward from the collapsing core. Most pass through the star almost effortlessly, but enough energy is deposited into the surrounding layers to help revive the shock. The explosion begins from the inside, but we do not see it yet, not immediately. The collapse has already happened in the core, but the outer layers do not know it at first. The star is so enormous that the disaster needs time to reach the surface. From our observation platform, the first sign may not be light. It may be neutrinos. The detectors wake. A signal appears. Not one particle, not a few, a flood. The platform systems recognize it before the visible star changes. Deep inside that distant giant, the core has collapsed. The supernova has begun. But outside, the star still looks calm. That delay is one of the most chilling parts of watching a massive star die. You know the core is gone before the star shows it. You know the death has already happened before the light arrives. The surface still shines like a living star. But inside, its heart has collapsed into something else. A neutron star, or the beginning of a black hole. The instruments record everything. Neutrino alarms rise across the panels. X-ray sensors prepare for the first shock breakout. Optical telescopes remain fixed. Spectrometers wait to read the elements that will soon be thrown into space. And the star, massive and ancient, hangs in the darkness ahead. It has no idea it is already dead. For a moment, there is stillness, a terrible stillness, the last calm before the universe opens. Then the shockwave moves outward through the star. It races through layers that took millions of years to build. Hydrogen, helium, carbon, oxygen, silicon, iron. The star's entire history is about to be thrown into space. Everything it created will be released. Everything it held will be scattered. The final second in the core becomes a blast that will shine across galaxies. This is the difference between the death of a sun-like star and the death of a massive star. The sun-like star fades into beauty. The massive star breaks. It cannot negotiate with gravity. It cannot settle into peace. Its core collapses too fast. Its outer layers are too heavy. Its fuel stages end too violently. And when the final failure comes, the entire star becomes a weapon of light. From 50 light years away, we wait, safe, but not untouched. The observatory is quiet, but every instrument is alive now. The star fills the screens. Its brightness is about to change. Its surface is about to be torn open from below. The shockwave is approaching the outer layers. This is the last moment before the visible death. The final image of the star as a star, still round, still glowing, still ancient and enormous, but already changed forever. Inside, the core has collapsed. Inside, matter has become neutron dense. Inside, neutrinos have escaped. Inside, the explosion is climbing toward the surface. The countdown has ended. The star's heart has failed. And now, the light is coming. The core does not collapse slowly. It does not hesitate. It does not fade like the dying sun-like star did. It falls. In a fraction of a second, the iron heart of the massive star gives way. The pressure that held it up disappears. The electrons that once resisted gravity can no longer support the weight above them. The star has spent millions of years fighting collapse. Now it loses that fight in less than 1 second. Deep inside the star, the iron core begins shrinking with terrifying speed. What was once a core, roughly the size of Earth, is crushed inward until it becomes only the size of a city. A whole stellar heart, compressed into a sphere only a few tens of kilometers wide. The density becomes almost impossible to imagine. Matter is no longer behaving like ordinary matter. Atoms cannot survive. The spaces inside atoms vanish. Electrons are forced into protons. Protons and electrons merge together, creating neutrons. And in that instant, the core becomes something new. A neutron star. Not over thousands of years. Not over days. Not even over minutes. In less than a second, the center of the massive star transforms into one of the densest objects in the universe. A newborn neutron star, a city-sized remnant containing more mass than the sun, a place where a teaspoon of material would weigh billions of tons, a place where gravity is so extreme that the surface would crush anything ordinary into something unrecognizable. But the rest of the star is still falling. The outer core and inner layers continue rushing inward at incredible speed. They do not yet know that the center has changed. They fall toward the newborn neutron star, pulled by gravity, collapsing into the place where the iron core used to be. Then they hit. The infalling material slams into the newly formed neutron core. And suddenly, the collapse rebounds. A shockwave is born. It begins moving outward through the star with unimaginable force. For one brief moment, it seems as if the explosion has already begun. But the star is too massive, too dense, too heavy. The shockwave loses energy as it tries to push through the falling material. It slows, it struggles, it nearly stalls inside the star. This is one of the strangest moments in a supernova. The core has collapsed, a neutron star has formed, a shockwave has begun. But the explosion is not yet guaranteed. The star is still fighting against its own death. Then come the neutrinos, trillions upon trillions of them. More than the mind can hold. They flood outward from the collapsing core in a ghostly storm. Neutrinos barely interact with matter. They can pass through entire planets as if the planets were almost empty. Most of them escape the star completely, carrying away an enormous amount of energy from the newborn neutron star. In that 1 second, the collapsing core releases more energy than our sun will produce over its entire 10 billion year lifetime. Almost all of it leaves as neutrinos, invisible, silent, unstoppable. From our observation platform, 50 light years away, the neutrino detectors wake first. The star itself still looks normal. On the screens, it is still a glowing sphere, still ancient, still whole. But the instruments are no longer calm. The neutrino signal rises suddenly, a flood from the core, a warning from inside the star. The observatory knows before the eye does. The heart of the star has collapsed. The supernova has already begun, but the light has not reached the surface yet. This is the haunting delay. We know what happened before we can see it. The core is already gone. The neutron star has already formed. The shockwave is already fighting its way outward. but the outer layers of the star are still hiding the event from view. The star's surface continues shining with the light of its final, normal moments. It looks alive, but it is not. Inside, the explosion is climbing. The shock wave, helped by neutrino energy, begins to revive. It gains strength. It pushes outward again, layer by layer. It tears through the star's interior. It moves through silicon, through oxygen, through neon, through carbon, through helium, through hydrogen. Every shell the star built across its life is now being ripped open from within. The star's history is being thrown outward. The elements it forged in its core and shells are about to be scattered into space. Oxygen, carbon, silicon, calcium, iron, everything that once belonged to the star is being prepared for release. This is not just destruction, it is distribution. A massive star does not keep what it creates. At the end, it gives it away violently. The shock wave keeps rising. The outer layers begin to respond. The surface starts to bulge. Pressure builds from below. The star's skin is about to break. From our platform, we wait. There is no sound in space. No roar reaches us. No thunder, no crack. Only data, neutrinos, radiation levels, spectral changes. The observatory is quiet, but the silence feels impossible because we know what is coming. Somewhere inside the star, the shock wave is racing outward. The light is trapped for the moment. The visible explosion is still hidden beneath layers of stellar gas. But not for long. Then the shock wave reaches the surface. The star breaks open. A flash erupts. This is shock breakout. The moment the explosion finally becomes visible, a sudden release of light and high-energy radiation bursts from the outer layers. The star's surface, once intact, is now being blasted outward. The death that began deep in the core finally reaches the universe outside. And then, a new star appears. Not truly a new star, a dying one. But from the outside, it looks as if a new sun has been born in the sky. A point of light where there was already a star becomes violently brighter. It rises in brightness with astonishing speed. The dying star begins to outshine itself by millions, then billions of times. From 50 light years away, our instruments flood with light. The observatory shields adjust, filters darken, sensors switch modes. The optical telescopes capture the brightening, but the star is no longer something safe to look at directly without protection. Its light is too intense, its radiation too fierce, its energy too sudden. The supernova has begun. If this were visible from a nearby planet, it could shine brighter than anything else in the night sky. In some cases, a supernova can become visible even in daylight, a point of light so bright that ancient civilizations would record it as a new star appearing in the heavens. But from our position, with advanced instruments watching every wavelength, the event is more than a bright point. It is an unfolding structure. The outer layers of the star are now racing into space. The shockwave carries them outward at thousands of kilometers per second. The star is no longer a star in the normal sense. It is an expanding explosion. At the center, hidden behind the blast, the newborn neutron star remains, small, dense, furious, a remnant of the collapsed core. Around it, the rest of the star is leaving. The star that once held itself together for millions of years is now becoming a cloud, a nebula, a remnant, a new source of elements for the galaxy. The brightness continues rising. The supernova becomes a beacon. For a time, it may outshine entire galaxies. one dying star can become brighter than hundreds of billions of ordinary stars combined. That is the scale of core collapse. A single second in the core becomes weeks and months of cosmic light. The energy moves outward. The ejector expands. The spectra change as different elements appear in the glowing debris. The observatory records hydrogen lines, helium lines, oxygen, calcium, iron, and heavier signatures. The star is opening itself like a book, showing the layers it built during its life. The death reveals the life. Everything hidden inside is now visible. But the most terrifying part is how fast the irreversible moment came. Millions of years of burning, thousands of years of later fusion stages, days of silicon burning, a fraction of a second of core collapse, and then the star was gone. Not vanished, transformed. The outside world saw a brilliant explosion, but the true death happened before the light appeared. The real ending was in the core, that invisible inward fall, that sudden compression from Earth-sized to city-sized, that instant when electrons and protons became neutrons, that moment when gravity won and matter became something extraordinary. From our platform, we watched the supernova grow brighter and brighter. The star that looked normal only moments ago is now the brightest object in its region of space. A new light in the sky. A violent flower opening in the dark, beautiful from far away, fatal from close up. The instruments keep recording. The neutrino signal fades after its first impossible flood. The visible light rises. X-rays and ultraviolet radiation pour outward. The shockwave expands. The dying star becomes a cosmic event. And in the silence of space, we understand what we have just witnessed. Not simply an explosion, not simply a star dying. We have witnessed gravity crushing a stellar core in less than a second. We have witnessed matter become neutron dense. We have witnessed the moment a massive star failed from the inside out. And now the universe is lit by the result. A star has died. A supernova has begun, and the darkness around it will never be the same. The light arrives all at once. For a long time, from our observation platform, the star looked almost unchanged. The instruments knew the truth before our eyes did. The neutrino detectors had already screamed. The core had already collapsed. A neutron star had already formed, or perhaps the first moments of a black hole had begun. But the surface of the star had hidden everything until now. Suddenly, the sky changes. A point of light that was once a star becomes something far greater than a star. It brightens violently, not like a sunrise, not like a flare, not like a planet reflecting sunlight. This is a star tearing itself open. The first burst of high-energy radiation crosses space at the speed of light. Gamma rays and X-rays rush outward. Ultraviolet light follows with terrifying intensity. Then the visible light rises, brighter and brighter, until the dying star becomes the most dominant object in the sky. From 50 light-years away, our platform survives. But survival is not comfort. The shields are active. The instruments are protected behind filters. The optical systems reduce the glare by thousands of times just to keep from burning out. Every detector is overwhelmed, then recalibrated, then overwhelmed again. Supernova is no longer just an event. It is the sky. A single point of light shines with a power that makes ordinary stars feel fragile. At peak brightness, this dying star may become billions of times brighter than the sun. For a time, it can rival the light of entire galaxies. One star, one death, a brightness so extreme that if there were a planet nearby, its night would vanish completely. The sky would turn white-blue. Shadows would appear in places that had never seen light from that direction before. The surface would be flooded with radiation. Atmospheres would be damaged. Oceans, if close enough, would be poisoned by high-energy particles, and chemistry changed in the upper air. From our distance, we are safe only because we prepared. But the universe around the star is not safe. The brightness keeps rising over hours and days. The first flash was only the beginning. The expanding debris grows hotter and brighter as the shockwave pushes through the outer layers and releases trapped energy. What was once a stable sphere of plasma is now an expanding cloud of destruction. Every wavelength tells a different part of the story. Gamma rays reveal the most violent nuclear processes. X-rays show the hottest regions where the shockwave slams through dense material. Ultraviolet light traces the fierce radiation from the newly exposed layers. Visible light gives us the beautiful, terrifying glow we would call the supernova in the sky. Infrared shows dust, cooling gas, and material beginning to form in the expanding remains. Radio waves reveal charged particles moving through magnetic fields, the invisible violence spreading long after the first flash has passed. The star is speaking in every language of light, and our observatory listens to all of them. The spectra change minute by minute. Lines appear, shift, strengthen, fade. Hydrogen, helium, oxygen, calcium, silicon, iron. Each element leaves its fingerprint in the light. The star is no longer hiding its interior. The explosion has opened it. For millions of years, the star built layers inside itself. Now those layers are being thrown into space. The elements are no longer trapped in the core. They are becoming part of the galaxy. This is one of the most important things a supernova does. It does not only destroy a star, it spreads the ingredients of future worlds. The oxygen that may one day become air, the silicon that may become rock, the calcium that may become bone, the iron that may become blood, and in the most extreme explosive environments where neutron-rich matter and violent reactions occur, even heavier elements can be created or scattered. Gold, platinum, uranium, and other rare atoms that require extraordinary cosmic conditions. Every gold atom on Earth has a story like this, not necessarily from one ordinary supernova alone, but from the deaths and collisions of stars, from violent stellar events where matter was pushed beyond normal limits. Gold was not born gently. It was forged in catastrophe. The ring on a human finger, the metal deep inside Earth, the rare elements hidden in rock, all of them carry the memory of ancient stellar death. That is what we are watching now. Not only an explosion, the creation of future chemistry. The shockwave expands outward at tens of thousands of kilometers per second, around 30,000 kilometers per second in the early blast, racing through space faster than anything human technology could ever approach. It sweeps through the material the star had already lost before death. Gas shells from earlier stellar winds are struck and heated. Older clouds of matter are compressed. Dust is shattered or formed again. The surrounding space is carved open by the blast. The star is cleaning its neighborhood with violence. Any planets close to it are gone as living worlds. Their atmospheres are stripped or chemically damaged. Their surfaces are sterilized. Ice is vaporized. Rock is irradiated. Moons become burned remnants. Entire planetary systems that once orbited this star are now inside the expanding fury of their own sun's death. If life had ever existed there, the supernova would be its final sky, a light too bright to survive, a dawn with no morning after. But farther away, the effect is different. The shockwave may compress nearby gas clouds. It may trigger new star formation. It may push dust and heavy elements into regions where future stars will be born. The death of this star may help create new solar systems millions of years from now. That is the strange balance of a supernova. Near the explosion, it is apocalypse. Farther away, it is creation. The outer shell continues expanding. At first, it is almost too bright to see structure. It is a blaze, a sphere of light, an expanding fireball. But as days turn into weeks, and weeks into months, patterns begin to emerge. The debris is not perfectly smooth. It forms knots, filaments, waves, and clumps. Some material moves faster, some moves slower. Some is rich in oxygen, some in silicon, some in iron. The explosion is uneven because the star itself was uneven, and the collapse at its core was not a perfectly clean event. The supernova begins to become a nebula, a supernova remnant, a glowing wound in space that will last for thousands of years. From our platform, we watch the first stage of that remnant forming. The expanding shell spreads outward, growing larger with every passing hour. The central brightness slowly changes. The color shifts as the gas cools and different elements dominate the light. The star is now gone. In its place is an expanding cloud, a new structure, a luminous memory. Over the next thousands of years, this remnant will continue to grow. It will slam into the surrounding interstellar gas, heating it, compressing it, and making it glow. It may become something like the Crab Nebula, the Veil Nebula, or Cassiopeia A, a beautiful remnant of a violent death, studied by civilizations long after the star itself has vanished. The supernova remnant will become a cosmic archive. It will show where the shockwave traveled, where heavy elements went, where the core collapsed, where the star's life ended. But the greatest mystery is at the center. What remains there? If the collapsed core stabilized, then a neutron star now sits inside the expanding debris, a city-sized object with more mass than the sun, spinning rapidly, wrapped in a magnetic field so powerful it can shape radiation across light years. If that neutron star is aligned just right, it may become a pulsar, a lighthouse in space, beams of radiation sweeping across the universe, flashing with every rotation. From far away, astronomers might see it blink again, 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 a heartbeat left behind by a dead star. But if the original star was massive enough, or if enough material fell back after the explosion, the core may collapse further. Then even neutron pressure cannot stop gravity. The remnant becomes a black hole. No surface, no light, no pulse, only a boundary beyond which nothing returns. In that case, the supernova has not only killed a star, it has created darkness. From our observation platform, we cannot know instantly which ending has happened. The debris is too bright. The center is hidden behind expanding material. We watch for clues, X-rays, radio pulses, gravitational signatures, the motion of gas, the shape of the remnant. A pulsar would reveal itself with rhythm. A black hole would reveal itself through absence, through matter falling inward, through jets or accretion if material remains nearby. Either way, the original star is gone. The massive blue-white giant that once burned for only 10 million years has completed its life. It lived fast. It burned fiercely. It built heavy elements in its core. It reached iron. It collapsed. It exploded. And now it has changed the galaxy around it. The supernova continues shining. For days, it grows. For weeks, it dominates. For months, it fades slowly. But even as the visible light weakens, the event is not over. The remnant keeps expanding. The radiation keeps traveling. The heavy elements keep spreading. The shockwave keeps moving into the galaxy. A star's death does not end when the light fades. It continues as motion, as chemistry, as dust, as future planets, as future life. From 50 light years away, we watch in silence. The screens glow with impossible data. The sky is still bright with the new light. The expanding shell is now visible as a growing structure, no longer just a point, but the beginning of a nebula. And somewhere at the center, hidden in the remains, there is either a neutron star spinning like a cosmic heart, or a black hole quietly opening in the dark. The supernova has begun. The star is dead, but its death is still creating the universe. The supernova does not end when the first flash fades. For weeks, the dying star remains brighter than almost everything around it. It shines with a power that feels impossible for one object. Then slowly, the light begins to weaken. Not because the event is over, but because the star is no longer a star. It has become debris. The outer layers are still racing outward, expanding into space at thousands of kilometers per second. The brilliant point of light begins to soften, spreading into a growing cloud. What was once a massive star is now an expanding nebula, glowing in colors that reveal the elements inside it: hydrogen, oxygen, sulfur, iron, calcium, silicon. The star's hidden interior has been opened and scattered into the galaxy. From our observation platform, the supernova slowly changes character. At first, it was too bright to look at directly. A violent point of light, a cosmic detonation. But now, as months pass, structure begins to appear. The explosion becomes a shape, a shell, a cloud, a remnant. The gas glows in different colors as it cools, expands, and collides with the surrounding space. Some parts move faster than others. Some regions are denser. Some filaments twist like burning threads. Shockwaves ripple through the debris, lighting it from within. It is no longer only destruction. It is architecture. A new object is being built from the death of the old one. This is what a supernova leaves behind: a glowing wound in space, a nebula that can shine for thousands of years. And we have seen this before. One of the most famous examples is the Crab Nebula. In the year 1054, a new light appeared in Earth's sky. Ancient astronomers saw it. Chinese astronomers recorded a guest star. Arab astronomers also noted the event. It appeared where no bright star had been seen before, and it was so bright that it could be seen in daylight for weeks. For 23 days, a dying star was visible even under the sun. At night, it remained visible for much longer, slowly fading over time until it disappeared from ordinary human sight. But the star did not vanish. Its light faded. Its remnant remained. Today, when we point telescopes toward that region, we see the Crab Nebula, the expanding remains of that supernova. It is still growing, still moving outward, still glowing almost 1,000 years after the explosion reached Earth. The Crab Nebula looks like a tangled cosmic flame. Filaments of gas stretch outward in red, orange, blue, and green. The material is not smooth. It looks torn, electric, alive with motion. It is the body of a star scattered across space, and at its center is something extraordinary. A pulsar, a neutron star spinning about 30 times every second, 30 rotations every second. Imagine an object with more mass than the Sun, compressed into a sphere about the size of a city, spinning faster than a kitchen blender, with a magnetic field so powerful that it sends beams of radiation sweeping through space like a lighthouse. That is what remains at the center of the Crab Nebula. The core of the dead star did not disappear. It collapsed into a neutron star. A neutron star is almost beyond imagination. It is what happens when gravity crushes matter so intensely that atoms are broken apart. Electrons and protons merge into neutrons. The core becomes an object made mostly of neutron-dense matter. The size is tiny compared to a star, only about 20 kilometers across, a city-size remnant. But the mass is enormous, more than the Sun, compressed into that small space. The density is so extreme that a small amount of neutron star material would weigh billions of tons. The gravity at the surface would be crushing. The magnetic field can be 1 trillion times stronger than Earth's. And if that neutron star rotates, and if its magnetic poles are not aligned with its rotation axis, beams of radiation sweep through space. Each time the beam points toward us, we see a pulse. Flash, flash, flash. That is why we call it a pulsar. Not because the star is actually blinking like a lamp, but because its beam sweeps past us again and again. A dead star with a heartbeat. From far away, the pulsar seems almost alive. A rhythm remains where a massive star once burned. It is not life, of course. It is physics, rotation, magnetism, radiation. But there is something haunting about it. A star dies violently and leaves behind a clock, a lighthouse, a signal. The core that collapsed in less than a second becomes one of the most precise natural beacons in the universe. From our observation platform, if the supernova we witnessed created a neutron star, we would begin searching for that pulse. At first, the expanding debris may hide the central object. The remnant is too bright, too thick, too chaotic. But over time, as the gas thins and expands, the center becomes easier to study. Radio waves may reveal the pulse. X-rays may show hot regions near the neutron star. Gamma rays may appear from the most energetic processes. The remnant becomes a laboratory. The dead star continues to teach us. But not every massive star leaves a neutron star. Some are too massive. Some cores collapse too far. If the remaining core is heavy enough, even neutron pressure cannot stop gravity. The collapse continues. The newborn neutron star cannot support itself. It falls inward again, and then something darker is born, a black hole. This is the other possible ending. No bright pulse, no solid surface, no lighthouse beam sweeping through space, only an event horizon, a boundary where escape becomes impossible. If the collapsing core becomes a black hole, the star's death has created a region of space where gravity has won completely. Matter can fall in, light can approach, gas can spiral around it, but nothing that crosses the boundary returns. At the center, our physics points toward a singularity, a place where our equations break down, where density and curvature become extreme beyond our current understanding. A black hole born from stellar death, a new darkness made from a star that once flooded space with light. In the first moments after the supernova, some material may fall back toward the center. Not all the star's matter escapes. Some gas slowed by the explosion or pulled by gravity, returns inward. If a black hole has formed, it may begin consuming that fallback material. The process can release intense radiation if the material forms an accretion disk. Gas spirals inward, heats up, and glows before disappearing. Jets may form in some cases, depending on rotation and magnetic fields. The black hole itself remains invisible, but the matter around it reveals its presence. The universe becomes one black hole richer and one star poorer. That phrase feels simple, but it carries the entire story. A star that once burned for millions of years is gone. Its surface is gone. Its core is transformed. Its planets, if it had any, are ruined or changed forever. Its light as a star has ended, but the universe has not lost everything. The supernova remnant continues expanding. The heavy elements continue spreading. The shockwave continues moving through the surrounding gas. Somewhere in the future, that material may become part of new stars, new planets, maybe even new life. The death is not an endpoint. It is part of a cycle. Stars are born from clouds of gas and dust. They shine, they fuse elements, they age, they die. And when they die, they return material to the galaxy. A sun-like star returns its outer layers gently, making planetary nebulae and white dwarfs. A massive star returns its material violently, making supernova remnants, neutron stars, or black holes. Both endings feed the future. Without dying stars, the universe would be poor in heavy elements. There would be hydrogen and helium, but not enough carbon for life. Not enough oxygen for water. Not enough iron for planets. Not enough calcium for bones. Not enough gold, uranium, or platinum for the rare chemistry of rocky worlds. The death of stars makes complexity possible. That is why watching a star die feels so strange. It is terrifying because it destroys, but it is beautiful because it gives. The supernova remnant in front of us continues to expand. Years pass, then decades. The bright central event fades, but the nebula remains. The gas spreads into the darkness, carrying the star's history outward. If a pulsar sits in the center, it continues spinning. Flash, flash, flash. If a black hole sits there instead, it waits silently, hidden inside the debris. Either way, the original star has become something else. Not gone, changed. From our platform, we look at the glowing remnant and realize that this is what remains after one of the universe's greatest endings. A nebula of scattered elements, a neutron star beating in radiation, or a black hole swallowing light. The star's life has ended, but its matter is not finished. It will drift, mix, cool, collapse again one day, and perhaps millions of years from now, in some distant cloud enriched by this explosion, gravity will begin again. A new star will form. Around it, dust may gather into planets. On one of those planets, oceans may appear. And maybe, one day, something alive will look up at the night sky, never knowing that the atoms inside it were born in this ancient death. The cycle continues. Light becomes collapse. Collapse becomes explosion. Explosion becomes nebula. Nebula becomes stars. Stars become worlds. And worlds may become witnesses. The supernova fades. The remnant glows. The center hides its final secret. And the universe moves on. One star poorer, but forever changed by what that star gave back. When we watch a star die, we are not only watching something far away, we are watching part of our own origin. Because the story of a dying star does not end with the explosion, or the nebula, or the white dwarf, or the neutron star, or the black hole left behind. It continues. It travels outward in the atoms released into space. It drifts through the galaxy as dust and gas. It becomes part of new clouds, new stars, new planets, and eventually, life. This is one of the most profound truths in all of science. We are made of star stuff. The atoms inside your body did not begin with you. They did not begin with Earth. They did not even begin with the sun. Many of them were forged long before our solar system existed, inside stars that lived and died billions of years ago. The calcium in your bones was shaped by stellar processes. The oxygen you breathe was made in stars and released into space by their deaths. The carbon in your cells, the iron in your blood, the elements that build your body and the world around you, all of them carry the memory of ancient stars. Some were forged inside stellar cores. Some were scattered by red giants. Some were blasted into space by supernovae. Some may have been created in even more violent events, where dead stars collided and the universe briefly became a factory for its heaviest elements. And then, after traveling through space for unimaginable lengths of time, those atoms became part of a new cloud. That cloud collapsed. The sun was born. Dust gathered around it. Planets formed. Earth cooled. Oceans appeared. Life began. And eventually, billions of years later, those same atoms became part of you. That means you are not separate from the stars. You are a later chapter of them. A star died somewhere in the galaxy, long before there was an Earth, and that death helped make your body possible. Without dying stars, the universe would be simple. Mostly hydrogen, mostly helium. A beautiful universe, perhaps, but not a rich one. There would be no rocky planets like Earth, no iron cores, no oceans, no carbon chemistry, no breathable oxygen, no calcium bones, no complex life, no human beings looking up and asking where they came from. Supernovae and dying stars are not only endings. They are the reason complexity exists. They are how the universe moves from simple atoms to worlds with mountains, oceans, forests, and mines. A star's death is violent from close up. It destroys nearby planets. It floods space with radiation. It tears itself open and scatters its body across the dark. But on the larger scale, that destruction becomes creation. The death of one star becomes the material of another. The collapse of one core becomes the birth of future worlds. The explosion that ends one system may enrich the cloud that creates the next. This is the cycle. Stars are born from gas. They burn. They forge elements. They die. They return material to space. That material becomes new stars, new planets, new life, and perhaps new eyes to witness it all again. It is tempting to think of death as the opposite of creation, but in the universe, they are often the same process seen from different distances. Up close, a supernova is an apocalypse. From deep time, it is a beginning. Up close, a red giant destroys the worlds nearest to it. From deep time, its released gas becomes part of the galaxy's next generation. Up close, a star's end is loss. From deep time, it is transformation. And that brings the story back to us. Every breath you take is connected to stellar history. The oxygen entering your lungs was once part of cosmic gas. The iron carrying oxygen through your blood was created in the deep story of stars. The calcium holding your body upright was built by the same universe that builds nebulae and planets. You are not made from something separate from space. You are made from space. The same laws that shaped a supernova shaped the atoms in your hands. The same gravity that formed stars formed the sun. The same chemistry released by dying stars became the chemistry of life. In that sense, we are the universe experiencing itself. The stars do not know they shine. The nebulae do not know they glow. The galaxies do not know they turn. But we know. We look up. We wonder. We remember. We give names to the things that made us. A dying star does not understand beauty, but we can watch its light and feel something. A white dwarf does not know it is the last ember of a sun-like star, but we can understand what it means. A supernova does not know it is creating future worlds, but we can trace the atoms and realize that its destruction became our existence. That is the strange privilege of consciousness. We are small, fragile, brief, but we are made of ancient material, and for a moment, that material becomes aware. The universe spent billions of years building stars. Those stars died. Their ashes became planets. One planet became alive, and life became conscious enough to look back at the stars and say, I came from you. One day, our own sun will die too. Not violently like a massive star. It will not explode as a supernova. It will swell into a red giant, shed its outer layers, and leave behind a white dwarf. By then, Earth as we know it will not survive. The oceans will be gone. The atmosphere will be changed or lost. The surface will no longer be home to anything familiar. If life or intelligence still exists in the solar system, then it will have to move outward, adapt, or leave. The sun's death will be the end of Earth's familiar story, but it will not be the end of the sun's matter. Its outer layers will drift into space. Its gas will mix with the galaxy. Its atoms may become part of new clouds. Far in the future, some of that material may help form new stars, new planets, maybe new oceans, maybe new life. A world billions of years from now, orbiting a star not yet born, may contain atoms that once belonged to our sun. And on that world, perhaps something alive will look up at its own night sky and wonder where it came from. It may never know. It may never know that part of its world came from a yellow star that once warmed Earth, a star that had planets, a star that had oceans nearby, a star under which human beings once lived, dreamed, feared, loved, and asked questions about the universe. But the material will continue. That is the deep comfort hidden inside stellar death. Nothing remains the same, but nothing is truly wasted. The star changes form. The nebula fades. The white dwarf cools. The supernova remnant expands. The atoms drift, and the universe begins again. Not from nothing, but from what came before. This cycle has no simple beginning that we can emotionally hold, and no ending that fits inside a human life. It reaches backward into the first stars and forward into futures beyond imagination. Every generation of stars gives something to the next. Every death becomes part of another birth. Every cloud carries memory. Every planet is made from older worlds of fire, and we are part of that cycle too. Tonight, as you drift to sleep, remember that the atoms in your body were shaped by ancient stars. You are the universe looking at itself. You are made from stellar fire, from old explosions, from quiet red giants, from nebulae that faded before the sun was born, and with every breath, you are part of the same cosmic exchange. Atoms arrive, atoms leave, they become air, dust, stone, water, life, and one day, far beyond anything we can imagine, they may become part of something new, a new star, a new world, a new ocean, a new living thing looking up into the dark. The star does not truly die. It becomes something else. Light becomes dust. Dust becomes worlds. Worlds become life. Life becomes memory. And memory becomes wonder. So sleep now beneath the light of a star that is still alive, and know that long before you opened your eyes, the universe was already building you in the hearts of dying suns.